So it's my pleasure to introduce Sang-hyun Kim from the Korea Institute for Advanced Study, and he'll be speaking about optimal regularity of mapping class group actions on the circle. Thank you.
Okay, thank you very much for the invitation. I'm just honored to give a talk, at least online, in this seminar. Today, I'd like to talk about optimal regularity of mapping class group actions on the circle. So for the first part, I'll talk about what are these concepts, optimal regularity or mapping class groups or actions on the circle, and what people are doing in the academia. And then in the second part, I'd like to be more specific about the problem and the strategy that we took. So this is a joint work with Thomas Koberda at University of Virginia and Cristobal Rivas at University Santiago at Chile. So let me first introduce the main player for today, which is manifold diffeomorphism groups. So that is, you take a smooth manifold and you just collect all the CR diffeomorphisms of M. So at first, it is not completely obvious whether they would really form a group, but it's a good chain rule exercise that such a set is closed under composition and taking inverses. So R equals 0, this is a homeomorphism group. So this is just collection of all the self-homeomorphisms of M. So preserving the topological structure. And if R is an integer, then it is just collect all the C1, C2, C3, and so forth, all the CR diffeomorphisms. So it is also the set of homeomorphisms preserving the CR structures of manifolds. So they form a group. Slightly less trivial is the case when R is a real number, at least 1. Then you take, if you consider, say, the integer part, K, and the fractional part, tau, then the notion of CR diffeomorphisms corresponds to CK, and the kth derivatives are tau Hölder continuous. So you can talk about C 2.1 diffeomorphisms or C pi diffeomorphisms and so forth. So slightly ambiguous, what is ambiguous here is say, so C, sometimes we consider Lipschitz, but we should not write that as a one Hölder continuous. Rather, we will write 2 plus Lipschitz sometimes. So there is a notion of a C2 where second derivatives are Lipschitz or 1 Hölder continuous. So for each real number, also there is a diffeomorphism group. So again, it requires some easy chain rule exercise and some computation to verify that this set is indeed a group. And I'll just briefly mention that. So this is a group. And when you are trying to prove that this is indeed a group, what you will have to use in the real number case is the map is concave. So then, and using this chain rule, you can prove that this is a group. Sometimes you consider even more general concept, which I will not go into today. But sometimes people consider C2 comma alpha, where alpha is a concave modulus. Some modulus function, like some function converging to 0 as x goes to 0. So there's even a more fine stratification of the diffeomorphism groups. So anyway, so if you have, so therefore you have diff0 homeomorphism group and diff1, diff2, and also not just these countably many diffeomorphism groups, you have uncountably many ones by considering the real numbers. And as I said, you can also consider concave modulus as well. So there are many diffeomorphism groups, and diff infinities obviously defined as the intersection of all diff k. And you can even further consider the group of analytic diffeomorphisms if M has analytic structure. And if say M is S1, then you can also consider PSL2R, the Möbius transformations, which act very nicely on the circle. So the theme that I'd like to address today is how are they, so what are they as groups, as abstract groups? What are group theoretic properties that these continuous groups contain? And slightly more specifically, we want to distinguish them. So how do they differ as groups if you vary the regularity or if you vary manifolds? So there are certain uniformity and diversity regarding these groups, regarding properties of these groups. So just for a notation, we consider a support of homeomorphism. Well, closed support of homeomorphism is the closure of the complement of fixed point set. So we sometimes say support, or sometimes we say F tilde, sometimes O, we mean just complement of fixed point set. It really depends on the choice of the authors. Sometimes, especially analysts reserve the SUPP for the closure of a support, but people in group actions sometimes often consider SUPPF as the complement of fixed point set. So anyway, so considering this, having this notion of the support, so let us consider a certain, in some sense, conceptually smallest subgroup of diffeomorphism groups, which is the set of all CK diffeomorphisms, which is compactly supported and isotopic to the identity, and slightly more strong requirement is that the isotopy must be compactly supported. It cannot be supported in the whole manifold, for example, in the middle time. So that is denoted as the diff KC0, and topologically, actually, this is same as the set of the identity component of the compactly supported CK diffeomorphisms, which requires a proof. So then, a famous celebrated result of Thurston for C infinity and Matter for CK is that this group is simple. So this is relevant to Thurston's effort to consider actually topology of this group, considering H1, H2, and so forth. So this group is simple for all k, which is either 0 or positive integer or infinity, except for the case that k is the dimension plus 1. And it is interesting to remark that the remaining dimension plus 1 case is still open, even in dimension 1. And that's right. If M is compact, then you can just disregard C. So you just consider all the diffeomorphisms isotopic to the identity. But the simplicity theorem holds for general m-dimensional manifolds, closed or not. So so for the most part, you can just imagine that the manifolds that I mentioned are compact. So another theme, so this is the uniformity. So every manifold diffeomorphism group is simple if you consider sufficiently small normal subgroup that you can conceptually define. The other extreme is the reconstruction theorem. The statements are due to Takens and Philip Kavitz. More precisely, Philip Kavitz stated the theorem and gave a proof, but it is the proof is dependent on an earlier work of Takens very significantly. So the statement is that if you have two manifolds, even possibly different dimensions, and two regularities, z plus or 0, and if the diffeomorphism groups are isomorphic as abstract groups, then everything should be the same. The regularities should be the same, dimensions are the same, and manifolds are CI diffeomorphism. And actually, this phi is induced from H. So phi is, well, H induces phi. So there exists diffeomorphism inducing the given isomorphism. So the conclusion is very strong. So at first it seems a bit mysterious because you have two groups, although they are very large, they are just groups. That means just a bunch of multiplication tables. So if you just compare only those multiplication tables, and then you deduce the topological structure and even differentials, even smooth structures. So CI smooth structures of the manifolds. So you can, so in some sense, I mean, in a precise sense, you can detect, say, exotic smooth structures of manifolds by their diffeomorphism groups. So this mystery can be explained in two directions. First of all, recovering the topological part is actually due to Rubins. Actually, Philip Kavitz gave a hands-on proof of this part, but the proof can be greatly simplified by a result of Rubin, which is proved about the same time. So let us consider, so Rubin defined the notion of local density. So group action on a space is called locally dense if it's locally every orbit is not nowhere dense. So this is some succinct way of expressing it, but more precisely this statement. So whatever point you consider and whatever open neighborhood you consider all the group elements supported only in that open neighborhood U. And consider the closure of the orbit. Then the closure of orbit must have some interior. So this is definition of orbit is not nowhere dense. So you have certain, whatever U you consider, whatever X you consider the group elements supported only in that neighborhood. And consider the orbit of it, then it should be not nowhere dense. So this might sound a bit artificial, but this turns out to be the right definition to prove desired result. So for example, a diffeomorphism group acts on M locally densely, because you can prove this by some partition of unity and some conjugation of vector fields, locally smooth, compactly supported smooth vector fields, for example. So then the theorem states that if you have two locally compact Hausdorff perfect space, you can just imagine that they are manifolds. And if G acts locally densely on these two spaces, then actually everything should be the same. There exists a homeomorphism, and this homeomorphism must conjugate these two actions. So this is precisely explaining the mystery that the group, just pure collection of multiplication table, can reconstruct the topology of manifolds. And it turns out that the condition local density is explaining this mystery. So for example, you can consider, say, Thompson's group. I'll just get back to this part later, but just sufficiently big subgroup of homomorphism group or diffeomorphism group can recover the topology of the manifolds. And the second part, now how do we recover the regularity? So again, yeah, so here perfect means just no isolated point. Just so what is it? Derived set is itself. Just every point is accumulated by something else. And the mystery regarding the recovering regularity can be proved by a more classical result by Bochner-Montgomery. So this is often attributed to Montgomery-Zippin regarding their solution to Hilbert's fifth problem, but I believe this is a wrong attribution, because the book by Montgomery and Zipping contains this result, but it clearly states that this is due to an earlier paper by Bochner Montgomery. So which tells us, well, actually the original theorem is more general, about general Lie group G. But for us, just the action of Rn is enough, and it's very easy to explain. So if suppose you have a group action by Rn on a manifold, and you know that the group is continuous, and it is ck for each vector. So I would call this as time-wise ck, considering Rn as the time. Or you can imagine that n equals 1, which is even already non-trivial. The time-wise ck, then the whole map is ck. So it's kind of asserting that the smoothness on the spatial derivatives are infecting the smoothness on the time-wise part. So it's regarding some mystery of this Lie group or Rn. So if it is time-wise smooth, then it must be just simultaneously ck, or if, for example, and then in particular time-wise ck smooth. So this explains the part of recovering the regularity. So you can, and then you can use this Bochner-Montgomery theorem to prove that the homeomorphism that you find using Rubin's theorem turns out to be actually CI diffeomorphism. Using that, each element you consider already CI or CJ diffeomorphism. So these are the two main ideas. As I said, Philip Cave didn't actually use Rubin's theorem, but Rubin's theorem can be used to give a much simplified proof, as Rubin noticed. So a more specific theme that I'd like to address today is now the whole group can recover the regularity and the manifold. Then what about finitely generated subgroups? Because as a geometric group theorist, I'd be interested in finitely generated subgroups rather than the whole continuous groups as abstract object, because the whole continuous group seems to be a bit large, and it is somewhat, in some sense, somewhat expectable that you can deduce a lot about the topology using the whole group or topology of the group. But what about finitely generated subgroups? Can you distinguish these groups by finitely generated subgroups of? And we focus on n equals 1 today.
Sam, just before you go on to discrete groups, can I just ask 2 questions?
Yes, please.
So the first one is, what structure do these diffeomorphism groups have? Should I think of them as something like an infinite dimensional Lie group or something like that?
Yes, they are not infinite dimensional Lie group in a precise sense, I believe. So that is some result regarding that, like by I think Miller proved something that it cannot be given an infinite dimensional Lie group in a precise sense. But yeah, so they have various structures. So for example, they have natural CI topology or like Whitney topology. So it is a topological group. So you can also talk about their homotopy type or homology groups, which are also very interesting and hard topics. I'm mostly focusing on purely abstract algebraic structures that they carry, namely as groups, and how much I can recover from the algebraic structures. And
so all the previous statements are just purely abstract group statements, like it's simple as an abstract group. And
yeah, that's right. Yeah, simple as abstract groups and isomorphic as abstract groups.
And the second question I was just kind of wondering about, because this group here, some of us love Lie algebras.
Yeah.
And
I
was wondering, like, how should I think about the Lie algebra of this group if it exists, etc. Of these groups?
I see. Yep. So that direction is, a bit distant from the thing that I'm taking today, I believe. So there are there is a. So I sometimes consider the metrics or topology on these groups are very useful, and also many foliation theorists consider these diffeomorphism groups for one of the reasons that I'm going to explain very soon. But Lie algebra part, that has also important ramifications, but I couldn't find the use of such an approach to deduce purely abstract group theoretic statements regarding these groups.
But I kind of imagine that like a vector field, I should think about as being an element of the Lie algebra.
Yeah, yeah.
Because like exponentiating the vector field gives me some diffeomorphism and.
Yep. So yeah, there's there are very interesting theories that I'm not very familiar with. There's a theory about, for example, Virasoro algebra for dimension 1 circles. So then if you have a diffeomorphism circle, then you can consider its central extension. Then you have consider the Virasoro algebra, and it has a very beautiful Lie algebra structures, I believe, and so forth.
Thanks.
Yeah. Thank you for asking.
I can jump in here with a question then as well.
Yes, please. Yeah.
So you say, so you're thinking about finitely generated subgroups.
Yes.
One could also, I mean, one thing that people like to do, especially with three manifold groups, is to look at finite quotients, really. Yeah. So to think about pro-finite completions. So would diff be too complicated a group to think about pro-finite completions, or?
That's a good question, but finite index subgroups are actually very rare in these groups. Very rare.
Yeah. Okay.
So first of all, they are simple. I mean, so if you consider the normal subgroup structures are in some sense completely known. So if you consider this the smallest diff C0, it is simple, and therefore any homomorphism from that group is either embedding or trivial. So I believe there are no interesting finite index subgroups. So I don't think you can take any meaningful pro-finite completion of these groups.
I see. So maybe you have to pass to a quotient or something, but then maybe the quotient is already finite anyway. Yeah.
So quotients are very rare. That's my point. Yeah, quotients are very rare, because that's that has been studied even earlier by Higman's technique, that if you have a sufficiently big group acting on a set, then the normal subgroups can be completely understood. Another interesting thing is to remark is that still people do not know whether diff2 of R is simple or not. So Metter found interesting homomorphism from diff1 whose first derivatives are bounded variation. First derivatives have bounded variations of compactly supported of real line into R. So there is a very interesting homomorphism, non-trivial homomorphism. So here you can have lots of finite index subgroups, for example, then lots of interesting normal subgroups.
Yeah. If I can just jump in on the finite quotients thing. So as soon as any group has a finite index subgroup, it has a finite index normal subgroup, because you consider the action of the group on the coset space, say G mod H, and then the kernel of that action is a finite index normal subgroup. So if it's an abstractly simple group, it's not going to have any finite quotients.
Thanks. Yeah, thanks. So regarding the some of the motival, I'll probably skip this part very quickly because we'll never use this in today's talk. But just briefly saying, many foliation theorists consider diffeomorphism groups for their own sake. One of the reasons is if you have, for example, codimension 1 foliation, you can, there's a, so that is, I'll just skip this part because we don't have much time. So I'll just say that Thurston stability. I'll just jump to the Thurston stability, which is to state that. So I'll just briefly mention that many foliation theories like Tzboy or Thurston or Metter or Gis consider diffeomorphism groups and their finitely generated subgroups because it's a close relation between finite general subgroups of diffeomorphism groups, especially manifold subgroups of diffeomorphism groups, and foliations based on such manifolds. And one of the most influential result in 1970s by Thurston is that if you have a compact, connected, transversely oriented codimension 1 foliations of a general manifold, and if you know that there's one compact leaf whose H upper 1 is 0, in other words, finite abelianization of the fundamental group, then you can determine the whole foliation. So this was quite striking. Then the whole foliation must be just I bundle or bundle over S1. So this is this can be considered as a whole classification of this codimension 1 C1 foliations, if you know the existence of some nice leaf, compact leaf. And if you look at the proof, the heart of the proof, the main idea, basically almost the only idea of the proof can be described purely in terms of one-dimensional diffeomorphism groups, which is to state, can be stated as that the C1 diffeomorphism group of closed interval or even half open interval is locally indicable. So some people in diffeomorphism group theory calls this as Thurston stability lemma, although I'm not completely sure whether that is the good terminology. So anyway, so locally indicable, what does it mean? It means that every finitely generated, so usually a statement regarding finite generated subgroup is called locally in group theory. So whatever non-trivial finite generated subgroup you consider, it's surject onto Z. In other words, it has an infinite abelianization. So Thurston stability lemma asserts that if you have a finite generated subgroup, so as we mentioned, the whole group does not surject onto Z, but if you consider any finite generated subgroup, then it's surject onto Z. So actually, one can use this to prove that many groups are locally indicable as well. And this is the key idea of proving the Thurston stability.
Sam, I'm sorry. I think that some students would not have seen what a foliation is. Could you just say quickly?
Yes. Well, I chose not to say anything about the foliation, but just the definition is that so CK foliation, what is it? It is an atlas on the manifold, so that the charts look like R n-1 cross R, so or I direction, R direction, and this is the R n-1 direction, the leaf direction. And then there is a restriction on the transition map. So on the overlap, the transition map only depends on, so on the transition map, the horizontal part must map to horizontal part. So this intuitive meaning is much more important than this more precise statement in formula. That is the vertical part. The transition of the vertical coordinate only depends on the vertical coordinate of the previous one. And then horizontal part, you can just move freely. And when you say CK foliation, usually transversely CK, meaning that the horizontal transition is C infinity or whatever you want, and the transversal regularity is CK. So this is a foliation structure, and this is somewhat in some sense, the main part of the study in differential geometry, in at least in 70s or before. So the point that I'd like to make was that foliation theorists consider diffeomorphism groups for their own goals. And for example, this Thurston stability theorem can be proved by a pure result regarding purely about finite generated subgroups of diffeomorphism groups. And so for example, you can consider n-chain group. So that is say FGH are graphs of 3 diffeomorphisms of interval supported on, say, first interval, second interval, and third interval. So this, obviously you can choose FGH as smooth groups. And one can ask, what are isomorphism types of these groups? That is a legitimate question. And one can say, again, there is certain uniformity and diversity of isomorphism types, but what you can directly prove that all these groups are locally indicable, which is quite non-trivial if you want to prove it directly. But these are all subgroups of C1 diffeomorphism groups of interval, so they are automatically locally indicable. Another example is so-called Thompson's group, which is collection of all PL homeomorphisms of compact interval, where slopes are powers of 2 and breakpoints are dyadic rationals. Then there are several ways of proving that these groups are actually C infinity. These piecewise linear actions can be conjugated to a smooth action on a compact interval. So therefore, they are automatically locally indicable. And
I have a couple of questions.
Yes, please.
In the definition of foliation, you say one codimensional foliation.
Yep.
That means you are separating only one component, right? Sorry, codimension one?
Yep.
Is related to the fact that you are separating only one component.
Yeah, that's right. Yeah.
Okay.
Yeah.
And
Sure.
the second one is what means transversally orientable?
Yeah, so that means you can orient the horizontal surfaces. And then you can consider the connected component of the horizontal planes, right? That means you consider this plane and consider the corresponding horizontal part on the red part and just take the union. So that gives you a leaf. And these coordinate charts, the orientations are preserved for the whole surface. And there's an interesting non-example that Thurston mentioned. So I'll just end my first part with this example. So consider the 237 hyperbolic orbifold. So this is 237 hyperbolic orbifold. So it is the two-dimensional topological surface given with hyperbolic structures where you have cone singularities of order 237. And so the orbifold fundamental group can be described as this so-called 237 triangle group acting discretely on hyperbolic plane. So this is Fuchsian representation. So, well, you can only consider this group presentation if you are not familiar with this triangle Fuchsian representation. So then Thurston considered the so-called cipher fiber 3-manifold based on this orbifold, where you have 3 singular fibers. The fundamental group can be written as this group presentation. And geometric topologically, it means that you have this orbifold, base orbifold, and there are 3 singular fibering circles, and around it you have like 2 rotations or 3 rotations or 7 rotations, rotations of singularity, and all the others you have just regular fibers. So let me focus on the group theoretic part only today. So if you have this 237 triangle group and consider cipher fibered 3-manifold having this fundamental group, then what he proved is that what he observed is that this group acts topologically on compact interval, but never by C1 diffeomorphisms. So the explanation goes as follows. So you can consider circle homeomorphism group and consider a central extension by Z. That can be identified with real line homeomorphism groups, which is integer periodic, because you are considering the commuting elements of one translations. And in this big group, you have a PSL to R, and the middle part now corresponds to PSL to R tilde, the universal cover of PSL to R. And then in this picture, you can put the Fuchsian representation of orbifold fundamental group and cipher fiber space. The fundamental group of L corresponds to subgroup PSL to R tilde. So the message of this computation is that, so it is very easy to compute the first homology of cipher fiber space in this case. That is, you just abelianize and see that, immediately see that it is 0. Therefore, by Thurston stability lemma, pi on L never embeds into diff1 of compact interval. Because Thurston stability should be locally indicable, but it just never surject onto Z. But PSL to R tilde is subgroup of homeo of R, and homeo of R is same as homeo of 0, 1 by obvious identification. Therefore, pi 1L embeds into homeo, but never C1. So this is what Thurston observed in his paper. And then we can consider now, given a group, like how smooth can it act on a manifold? Sometimes it can act on C1 but not by C2, C2 but not by C3, or C2.7 but not C2.8. So can you consider such questions? So that is the theme that I'd like to address in my second part. Thank you very much.
It's an absolutely extraordinary argument, but I missed why. So you said that I1 of L was not locally
right.
by something which I missed.
Oh, it's by just easy computation. So you just abelianize. Yeah, it is a fun exercise. If you abelianize this group, then A square is ABC, implies A is BC, for example.
Oh, sorry. So it's just got no Z quotient, so it can't. Okay.
Right. And then you.
I see. That's what.
It's a fun exercise, yeah.
Mm-hmm.
And then you read that A equals B equals C equals 1.
And the other thing that I didn't get was you said pi 1 of L injects into homeo 0, 1. Oh, you're saying that homeo closed interval is because I can see it injects into homeo open interval 0, 1.
Right. So that is the same thing. So then this is same as homeo of open interval.
Course.
And then this is isomorphic to homeo of closed interval, assuming orientation preserving.
Mm-hmm.
Right, everything is orientation preserving. Yeah. Thanks for pointing that out.
One more question, if I may.
Yeah, please. Yeah.
You have this bonkers dim m plus 1. Like, what the hell is going on there? Like, why can't we decide that it's simple when it's ck for k equals dim m plus 1?
Oh,
like, what is the reason for this particular?
So, I mean, that is actually a very good question. But one will have to go into the detail of the proof of matter to see why that case is left out. So it depends really. So
it just for R. Why is C2 so hard just for R?
Right. So it's not precisely because of some mathematical reason, but rather a technical reason. So it depends on matter's approach. So let me see what I can say. So you want to show that diff k is simple, or diff k C0 is simple. So what matter? So matter wrote basically like 3 papers. So first part is when k is less than dimension m plus 1, and second is k is larger than dimension m plus 1. And the idea is quite simple. That is, you consider, if you have a diffeomorphism m, then what he considers is certain operator, say phi, from diffeomorphism sum, say in diffeomorphism. And this should be precompact. And then, so the key part is that this V is mapped into V. So it has certain contraction property. And then using fixed point theorem that phi of U is U. So F, it depends on F. And then the key property of this operator is that it, so F, and for any U in the diffeomorphism, consider FU and apply this operator. So certain V. All right, and then he considered actually fixed point of everything. So actually it is norm reducing. So then if you, so U is input. So F is fixed is F is given. And for any U, you map it to FU and apply operator to become something else. And then find the fixed point of this thing, and then end H1 preserving. Then what you get is the fixed point U0 is same as V of U0, but this is same as FU0 because it is H1 preserving. Because VU and FU have the same H1. So you conclude.
So the subscript 0, is that the identity component of your diffusion?
Oh, sorry. So is fixed point. So find. So this is psi. So then everything is norm reducing. You prove.
No, sorry, when you write diff KC M0.
All right, that is the identity component.
The identity component.
Yeah,
Yeah.
but here, so U0 is fixed point of psi by Tikhonov-Hölder Banach fixed point theorem.
And so an F is any diffeomorphism that you take.
Yes.
And then
Yes, but you fix it.
Yeah.
Yeah.
So F may not be in the identity component, but then you have this operator.
So everything is very near from the identity, I assume, just for technical reason. You assume everything is very near from the identity. So V is also sufficiently small neighborhood of identity. You prove that that is sufficient for our purpose. And right, so the point is that there is some operator, let's call it this measure operator, which is norm reducing, actually norm not just preserving but reducing a lot. So given some identity neighborhood of the diffeomorphism group to itself, reducing the CK norms. And consider the composition, whatever you consider in V, multiply by F, multiply means composition, and apply this operator. And matters operator preserves H1 class. So therefore, H1 preserving implies that VU0 and FU0 are the same H1 class. And this is just identity. So that means U0 and VU0 are just identity as diffeomorphisms, identical as diffeomorphisms. Therefore, you have U0 class and FU0 class are the same in H1. So then you conclude that F class is 0 in H1. So this shows that diff is perfect.
The identity component, but isn't that a normal subgroup in the diffeomorphism group?
That's right.
Yeah,
That's right.
yeah.
So the conclusion is this is simple.
Yeah, this one is simple, but
I didn't say that whole diffeomorphism group is simple. This.
Yeah, sorry, that was a misunderstanding. I thought you were talking about the whole diffeomorphism group.
Oh, sorry.
You're talking about the identity component.
Yeah.
Okay.
Yeah.
Sorry. No.
Yeah. So to go back to the original question. So why does this dimension bound matter for us? The reason is that when defining this matter operator, the norm reducing condition is closely related to this dimension and regularity bound. Because this operator is defined also using K. And then so consider the kth derivatives and just do some of, I cannot explain in detail in a very short time, but this norm reduction technique is closely related to dimension restriction. So there is an archive paper, archive preprint that I wrote with Thomas Koberda and a student that worked out all the details of matters proof for dimension 1. And I think that is, if anyone is interested, you can take a look at that paper. So matters paper is quite condensed. If you already know what he's talking about, then it's very well written. But if not, so it requires a lot of details and computations, which might have been trivial to mature already.
Was not clear to me if the case when K equals the dimension plus 1 is an open problem or is not known that is simple, or is known that is not simple.
It's not known. People have no idea. I really don't know where to bet.
At least is the answer clear for R or not either? For diff2R?
Yeah, but it's not known. It's not known. Yeah, diff2R of the compactly supported part of it. So obviously, compactly supported diffeomorphism group is a proper normal subgroup of whole diffeomorphism group. Right. So we can talk a bit more about this regularity of a group. So, for example, if you have a nilpotent group, then there's also plenty Thurston theorem in this direction. That is, every nilpotent subgroup of diff2. Yeah, Plenty and Thurston proved in 1976 that every nilpotent subgroup of C2 diffeomorphism group of compact interval or S1 is abelian. So nilpotent's degree is greatly restricted. So for instance, you can consider this class 2 nilpotent group, Heisenberg group, where you can ones are on the diagonals and upper parts are all integers. So more precisely, you have like 3 z's, just abbreviated as just 1 z. So this group may act on the interval, but it can never act by C2, by Plenty Thurston theorem, because it's not abelian, but nilpotent. And actually, Farber and Franks constructed a nice section of Heisenberg group, or even more generally, this class D nilpotent, universal nilpotent group, so-called. So it acts on the compact interval by C1 diffeomorphisms. And if you look at their paper, the construction of the topological part of the construction is very natural. We just consider action of ND plus 1 on, say, D minus 1 vector space by matrix multiplication, and use such vector multiplication to construct interval permutation and show that it is faithful action. So what is non-trivial is you just specify the lengths of subintervals to make the action to be C1 smoothable. So this is so therefore actually they proved even more strongly that every finitely generated residually torsion-free nilpotent groups acts by C1 diffeomorphisms on the compact interval. So by residual property, we mean that every non-trivial element survives in some torsion-free nilpotent quotient of the group. So Farber and Franks, by considering this ND plus 1 action and concatenation of such actions, they prove that every residually torsion-free nilpotent group acts by C1 diffeomorphism of the interval, and such groups are, for example, so therefore Heisenberg group, for example, acts by C1 diffeomorphism of the interval, but never by C2. So it acts by C1 by Farber and Franks, but never by C2. And one of the key examples that I'd like to address today is a writing the Artin group, which is defined by a graph. So if you have a finite simplicial graph, then the writing the Artin group is group presentation where vertices are generators, and whenever you have an edge, you declare the vertices of the endpoint. The endpoints are commuting. So for instance, if you have a triangle, you have Z3, 3 discrete vertices, then 3 generators, no relators, therefore F3. And if you have a wedge, so then you can consider Z part joined with the other 2 parts, which generate F2, so you have a direct product. So this group is known to have a variety of subgroups, a lot of subgroups. So for example, so one result that has been known in 1980s is that every subgroup surject onto Z. And actually you can say more strongly that every subgroup, every non-abelian subgroup surject onto F2 these days. And Ian Agol and Danny Weiss proved that every finite volume hyperbolic 3 manifold admits a finite index subgroup of the fundamental group embeds into some writing the Artin group. So you can immediately deduce that the virtual first Betti number is positive because G as a subgroup writing the Artin group must surject onto Z. And the relation of today's theme is that writing the Artin groups are residually torsion-free nilpotent, which has been known in 90s, which can be proved again by Ian Agol's notion of residually finite rationally solvable. So the point that I'd like to make is that the hyperbolic 3 manifold group virtually embeds into writing the Artin group. Therefore, it acts by C1 diffeomorphism group on the interval by Farber and Franks. So nilpotent groups have a C1 action. And there are many other residually torsion-free nilpotent groups which are geometrically important, like pure braid groups or Torelli group of mapping class group of surfaces. Yeah, virtual. Where did I say virtual? Right, so virtual Betti number. I was kind of hasty about this definition. So this is like, so what do I mean? So I am just saying that some finite cover of M has positive first Betti number. That's it. So this, yeah, just disregard what I said here. Yeah, I don't just abbreviate that sentence. So now you can talk about the precise real number optimal regularity of groups, finally. So we use the notation L following third sense. So this group, cipher fiber 3 manifold group, so-called A square B cube C7 ABC group, embeds into diff 0, but never into C1. It never admits any abstract embedding into diff 1. So similarly, Heisenberg group or many writing the Artin groups. Some writing the Artin group embeds, but we'll see that many writing the Artin groups embeds into diff 1, but never admit any abstract injective homomorphism into diff 2. So one can try to determine the precise regularity that these groups embed. That means given a group, you can consider the critical regularity of a group with respect to some manifold M as the supremum of the real number R, such that G admits injective homomorphism into CR diffeomorphism group in the manifold. So recall that we have defined the diffr for real numbers using Hölder regularity, just or this Hölder norm. Then there are several results in this direction. So Castro, Hoquera, Navas in 2014 proved that Heisenberg group has critical regularity precisely 2. That means, what does it mean? It means that Heisenberg group admits diff of C 1.9999, for instance. So it depends on the regularity. For each real number less than 2, there is the injective homomorphism depending on the regularity into diff 1999, 9999, and so forth. So it can get as near as 2, but never 2. And they also determine the critical regularity of this 4x4 upper triangular unipotent matrices. And it is precisely 1.5. But they couldn't determine whether it embeds into 1.5. They just proved that embeds into 1.499, but never embeds into 1.501, and so forth. And then we discovered examples of finite general subgroups. So for one manifold, so if you have I or S1, compact connected one manifolds, then for each real number R, right? So then we prove that for each real number R, there exists finite general groups GR and HR such that GR embeds into diffr, but never higher. It never admits injective homomorphism into diffs for S any larger than R. And HR is similar. HR is a subgroup of all the diffeomorphism group of smaller regularity, but it never embeds into diffr. So it is HR may be said barely CR smoothable, or just GR is just CR smoothable in some sense. So in particular, there exist finitely generated groups whose critical regularities are precisely R for each real number R. So this gives you a quick proof that there exist uncountably many distinct isomorphism types of finitely generated groups, of course, which can be proved by many other means. And one may ask, like, what some of these groups can be finitely presented? I do not know, but we know that almost surely these groups will never be finitely presented because there are only countably many finitely presented groups in the world, but we have uncountably many real numbers. So many of these will be never finitely presented.
I have a question about the theorem. In your theorem, the critical regularity is a maximum, not just a supremum, right?
It's a very good question. So in this case, it is maximum. Maximum is attained. So it is, but in this case, the maximum is not attained. So
one other question, is the proof constructive in some way? Like, can you nail down the GR and HR?
Yes, it is almost constructive. Yeah, it is constructive because yes, we nail down all the generators, and then the actions. Yeah, all the generators as just define the generators by their actions. We use some functional analytic existence result, but that is, yeah, that is constructive. That is, we just define that the function as a limit, but the limit is quite explicit. So yeah, one can say that it is constructive. We didn't really use functional analysis as just abstract some fixed point theorem. Rather, we just define the actions precisely as an infinite sequence, and we just use functional analysis to prove that this infinite sequence gives you a CR diffeomorphism.
Okay, thanks.
Yeah, thanks for asking. So today, the question that I'd like to address is closely related to the critical regularity of writing the Artin groups. So, and also it's relevant to critical regularity of finite index subgroups of mapping class group that I will explain soon. So why do we care about critical regularity of mapping class group or finite subgroup with acting on one manifold? So that has some origin in Nielsen's definition of topological action of mapping class group on the circle. So consider a hyperbolic surface and consider a base point, say x naught, and take any self-homeomorphism of a surface fixing the base point. Then you can lift it to the universal cover, right, which is H2. So lift it to the universal cover. Well, usually lift is only defined up to deck transformation, but here we fix a lift of the base point as well, so that the lift is uniquely determined. And one can prove that this is a quasi-isometry if the surface is compact. Quasi-isometry of H2, therefore by general theory, it defines a unique optohomeomorphism action on the boundary of H2, which is circle. So this is so-called so if you define mapping class group as the group of homeomorphism up to isotopy or quotient by identity component, then this gives you well-defined embedding, as Nielsen observed, into circle homeomorphism group. So this is a so-called mapping class group of a surface with one mark point or one puncture. So then the question is, how smooth can it be? So mapping class group this is a geometrically very natural action. So can you make it C1 or higher? So actually the answer has been found in early 2000. So Farber and Franks proved that the whole group can never act by C1 diffeomorphism group on the interval or the circle. And so Farber-Franks result has some genus restriction, so that has been strengthened by Parwani. And then recently, Katie Mann and Maxim Wolf gave out the different, more complete proof of the result by actually classifying all the topological action on the circle of mapping class group. And these results all use some toxic relations or torsions in the mapping class group. But all such things, torsions or certain braid relations and so forth, disappear in their deep finite index subgroups. And it is still a mystery to understand algebraic properties of finite index subgroups of mapping class groups. So let me skip a bit. And then, so people are interested but not making much progress toward the virtual properties of mapping class groups, which I realize is showing a frozen screen. Right. So one of the most remarkable conjecture in this direction is that for genus higher than 2 or 3 or higher, people want to know whether every finite index subgroup has trivial, so finite abelianization. So that means the question is, does the mapping class group have some finite index subgroup surject onto Z? Or I should say surject. Or mapping class group can never virtually surject onto Z. So that is the Ivanov conjecture. Every finite subgroup has finite abelianization, in other words. A relevant question is that mapping class group can never admit faithful C1 action on the circle or interval. So M1 is circle or interval. You can just imagine that it's circle. So this is a relevant question. And another question, we really shouldn't call this as conjecture. A question is mapping class group whether has whether mapping class group has a property T or not. In other words, every isometric action on a Hilbert space fixes a point. And these three questions are closely related. So using the Thurston stability lemma that I described in the first part, then one can actually deduce part 2 from part 1. So if Ivanov conjecture is true, then mapping class group will never admit faithful C1 action or circle or interval. So for the interval, it is precisely Thurston stability lemma. For the circle, you have to consider, you have to add a bit more argument, which is well known. And part 3 implies part 1. So it is also very standard in the theory of property T, that if you have a property T group, then it is finite abelianization. So 3 will imply 1. And also property T descends to finite index subgroups. And part 3 almost implies part 2, but not in this precise sense. So if you have property T, then it is known that G never embeds into C1 diffeomorphism group interval or C1.5 diffeomorphism group circle. So this is based on somewhat mysterious ideas of Reznikov and more precisely proved by Navas, and also Bader-Furman Gelander Monod gave a contribution to strengthen the regularity bound. But it is still unknown whether property T group can embed into even homeo. All right. So natural conjecture is it never embeds because there are no known examples of property T group embedding into S1. So these are all very intriguing virtual questions on mapping class groups.
Sam, can I interrupt again to display
Please,
my ignorance? So if I take, let's say, a genus 2 surface, and I fix my x0 as you did on the previous slide, and I do a Dehn twist,
Yep.
and then I lift this up as you explained to hyperbolic to a self-diffeomorphism of the hyperbolic plane.
Yep.
So I always assume naively that this would be some kind of hyperbolic transformation, but you're saying it cannot be made C1 on the boundary.
Yeah, that's right. It is
That's bonkers. I never realized that.
Right. So you have for example, you have some earthquake maps along these lines, right? You have one click slice for each all these curves, and yeah, this gives you some unsmoothness, and which cannot be simultaneously smoothed by one homeomorphism. So maybe one homeomorphism, one homeomorphism can obviously topology conjugate this action to a smooth action, but one homeomorphism cannot simultaneously conjugate all these dentists into C1 actions. That's the point.
Thank you.
Yeah, thank you for asking. So, right. So the main result that I'd like to address today is the critical regularity has been already defined. So I'll just skip the definition. Is that so? This right-angled Artin group, very specific right-angled Artin group, F2 cross F2 star Z, never embeds into diff1 tau of M1 for any tau. I should say plus tau. So by Farber and Franks, all the right-angled Artin groups embed into diff1, but the smoothness can never get any better. So that's the theorem for these groups. So critical regularity of this group is 1, for instance, in particular. And so there are many right-angled Artin groups containing this group. And of course, many other right-angled Artin groups not containing this one. So corollary is that most mapping class groups will never virtually embed into diff1 tau. So whatever finite index subgroup you consider, the mapping class group can never embed into diff1 tau. So the reason is actually this mapping class group contain that right-angled Artin group. For example, if genus is 2, then you can consider the red curves, pair of red curves and pair of blue curves. And if you consider then twist along these 4 curves, they generate F2 cross F2 if you raise them to high powers. And you consider 5th curve, which is complicated enough. Say, pick a simple closed curve and apply many powers of pseudo-Anosov. And they will intersect very complicatedly with these 4 curves. So along with this purple curve, you get copy of F2 cross F2 star Z, free product with Z. And what is nice about writing the Artin group is that, so if writing the Artin group, say A gamma, embeds into any group, and take any finite index of group H, then there exists embedding of A gamma into H as well. More precisely, if this was generated by, say, Vi, then you just consider Vi to the very high power. Then this will be isomorphic to A gamma. So whatever finite index of group you consider, it still contains a copy of writing the Artin group. Not the same writing Artin group, but copy of writing the Artin group. Therefore, any finite index of group mapping class group contains a copy of F2 cross F2 star Z. Therefore, it never acts by C1 tau. So regarding the 3 conjectures that I mentioned, I do not know any answer because we couldn't resolve C1. But you can say that at least it doesn't embed C1 tau. And it conspicuously misses the single case that F2 cross Z star Z, so we do not know the answer. And it is relevant to our ignorance regarding complexity 2 case. So complexity 3 or higher, so you can consider, say, genus 2, but genus 1 with 2 puncture, we do not know the answer. I'll say a few words about the proof. What are the key ideas? So key idea, so basically, so everything reduces to this single writing Artin group. So we just want to know whether F2 cross F2 star Z embeds into diff1 tau or not. Or more generally, we consider some G cross H star Z. So first of all, so we know sufficiently much about G cross H, let me explain where this star Z comes from. So that is what we named as ABT lemma that we proved earlier. So that can be stated as follows. So suppose you have a 3 C1 diffeomorphism group, 3 C1 diffeomorphism of compact 1 manifold. So M1 is always I or S1. So considers 3 C1 diffeomorphisms of compact 1 manifold. And the only assumption is that A and B have disjoint supports and T is anything. For example, we have A supported in these intervals. And say B is supporting this interval. Usually the supporting intervals can be very complicated. It may have many accumulated points as well, which is fine, which is common. And for T, you have no restriction. T, you may have many accumulated points. It doesn't matter. Then the conclusion is that these 3 diffeomorphisms will never generate Z2 star Z. So in general, if you have 2 diffeomorphisms having disjoint supports, it is natural to expect that they generate Z2. Well, in some rare case, they may generate say if A or B may be trivial, so they are maybe a subgroup of Z2, or sometimes on a circle, A is a rotation, then B is trivial. You might have some finite cyclic group. But anyway, so you may imagine that A and B generate Z2, or certainly it is abelian. But whatever T you consider, the point is that there is always a hidden relation between A, B, T. So you really have no restriction whatsoever on T, but there is some hidden relation coming from C1 regularity. So actually you can write down the relation. So if you consider some iterated conjugations and commutators, then what one can prove is that for this very specific word, the image have a compact support. So if you take the consider support of all the groups, say A, B, T, looks say something like this. It may have accumulated fixed point, accumulated support, which is fine, but T, the U0, will be supported in some proper subset of it. So closure must be contained in this open set. And using this, you can find some commuting relations. So this gives you some iterated commutator from U0 is trivial. So one can show that. So this is somewhat resembles, say, proof of classical Zariski theorem that if you have a certain nilpotent group, you have a certain small identity neighborhood which contains no non-trivial element, because if you have if you take commutator and commutator and commutator, then the norm reduces, for example, or in this case, the it simplify the diffeomorphism. So this is one of the main idea. And the second ingredient comes from the new observation, inspired by Navas' earlier idea, that if you have two, say, non-solvable groups, you may assume that they are non-solvable. And if the direct product acts by C1 tau diffeomorphisms on the interval by faithful diffeomorphisms, then very deep in their solvable series, the supports must be disjoint. So it is a simple exercise to deduce the whole theorem from only these two, right? Then now suppose you consider G is F2 and H is F2. Then you can suppose F2 cross F2 star Z embeds into diff1 tau. Then you can find some element in here deep in the solvable series, some element here deep in the solvable series, such that support of G and support of H are disjoint. Say non-trivial, for any element it's non-trivial, by the lemma that I just described. But this violates the ABT lemma, because whatever you consider here and whatever you consider here, it can never generate Z2 star Z. It can never, there is always a hidden relation with a new diffeomorphism. So the main theorem is an easy consequence of these two lemmas. And so I always assume that tau is positive. So I do not know so in this case, right, here tau is always positive. In the main theorem too, tau is always positive. So as I said, I do not know the answer for tau equals 0, which is closely related to Ivanov conjecture. So then the proof of this second lemma is related to, divided into two cases. So the first case is there exists some crossing of the supporting intervals. So there is some G1 and G2, and the supporting interval have some crossing. That means neither is contained the other, but non-trivial intersect. And the second case is that such a thing never occurs. Always supporting intervals of two diffeomorphisms, component of supports of two diffeomorphisms are always either disjoint or one is contained in the other. So in these two cases, the proofs are quite different. So in the first case, there are several studies in this direction, and people found, like Bonatti, Wilkinson, Crovisier, or Deroin, Klapps, and Navas in a slightly different argument, that they can find hyperbolic fixed points, so some element, group element, and some fixed point, say x0, such that g0 prime of x0 is not 1. And this pattern repeats by h because they commute. So so you see h x0, h square of x0, h cube of x0. By chain rule, you can see that the g primes are all the same. But xn moves to the boundary, which is a contradiction. Because on the boundary, one can show that derivatives are all 1. So the key word is there is the hyperbolic fixed point for some element. And for the second case, it is called the Conradian ordering or Conradian action, where there are no crossings whatsoever. And there is a well-known distortion argument prohibiting such a direct product, which is due to André Navas in his 2008 paper. So I think I'll stop here. Thank you very much.
Thank you again. Are there any other questions that people would like to ask?
Can you say a few words about why G equals 2 was excluded from the conjecture, the 3 conjectures you described before?
Oh, G equals 2, right. So G equals 2, all of these are known. So Ivanov conjecture is known for G equals 2 to be, so this is known for G equals 2. For this C1 smoothability, virtual C1 smoothability, actually I do not know. So yeah, so that is right, even G equals 2, I do not know the answer. Yeah, so this is a legitimate question. And property 2, I have to check. I'm not sure. But for this part, I can confidently say that G equals 2 case is not known. And this case, Ivanov conjecture is known in this case.
Great, thanks.
Just can I ask a question back on the Thompson group?
Yep.
So I think I missed the point there. So are you saying this is a simple group and therefore does not admit a map to Z and therefore is not indicable? Or what was the point of Thompson's?
Oh, all right, Thompson's group. So I mean, so that's kind of again overkill. So normal subgroup structure of Thompson's group F is well known. For example, its commutator group is simple and every proper quotient is abelian. But one quick way of proving that Thompson's group is locally indicable is that you prove that Thompson group F embeds into diff1 of 0, 1. So corollary is that F is locally indicable. So one can prove this directly using algebraic properties of Thompson's group, but one quick way is deduce it from a theorem that Thompson's group F embeds into C infinity diffeomorphism group interval. And actually, one can show it is not hard to see that actually Thompson's group F is isomorphic to the group generated by 2 diffeomorphisms F and G supported on say 0, 2/3 and 1/3 and 1 for some F and G. So obviously you can just pick 2 bumper functions.
Thank you.
Welcome.
Could I ask a question? So apart from right-angled Artin groups and mapping class groups and their subgroups, are there any other classes of discrete groups that you've thought about for this kind of question, or that other people think about even?
Yeah. So right. So I mean that is a very good question. So we mostly thought about writing the Artin groups for the purpose of application to mapping finite index over mapping class groups.
Mhm.
And there are people who studied other groups such as the nilpotent groups, as I mentioned. And some people consider hyperbolic three-manifold groups. So hyperbolic, say fibered hyperbolic three-manifold groups can be considered as subgroup of the once functional mapping class group that I just described. But the whole once functional mapping class group never acts by C1, as I mentioned.
Mhm.
But the smaller group, three-manifold group, can act by C1. So that is a recent result by Nicholas Tolotsan. But one can show that it can never act by C2. Yeah, that's about it, I think. Okay. And property T group, as I mentioned, it is an outstanding question whether it can act by even C0. It's quite intriguing.
Thank you. Right. Well, I think we've finished the questions. So let's thank Sam again.
Yeah, thank you very much. Thank you very much for the invitation.